Hi there, welcome back to Let's Design a Drug. This will be part 2 of a I don't know how many part installment, and let's get going. So, what we're going to talk about today is more so we talked about how to look at protein structures in Maestro. We're going to talk about now how to prepare those proteins to get them ready for modeling various types of drugs at the receptor target to see if we can build a drug that binds to our target protein, being the cannabinoid type 2 receptor. So the first thing we want to do is open up a internet browser. I use Chrome. That's totally irrelevant what internet browser I use. But anyways, the first thing we need to do is a lot of times when you grab a structure, as we talked about from the protein data bank, there are fake regions of protein that are used to stabilize the structure in order to get a crystal structure. What we kind of want to do now is, it's not necessary, I personally like to do it, is replace those fake regions of protein with the real amino acid sequence of that part of the receptor. To do that, we need to know the sequence homology, or the what amino acid is attached to what amino acid in all of the CB2 receptor. To do that, I like to use UniProt. Actually, I can just show you how to get the server. UniProt, this link, and you're going to use this top link called uniprot.org. In the search bar of UniProt, here you can search any receptor target or anything that has a known amino acid sequence. So this is a lot more comprehensive than the protein data bank. So we need the cannabinoid receptor 2. We can search, we have it here. 1, 2, okay. So what we're looking for is protein name. This is cannabinoid receptor 1. This is the mouse receptor. This is the cannabinoid receptor 1 rat. Human receptor for CB2. Basically, because we're trying to model how a protein docks to a human receptor, we want to use the human cannabinoid type 2 receptor. What we said is that although these types of GPCRs and any receptor does occur among many species of humans and animals, they will differ slightly based on what animal species genus they are in. So the idea here is that a CB2 receptor in a human is different from a CB2 receptor in a mouse, which is different from a rat, and so on and so forth. And this accounts for all of that. So we're looking for CB2 receptor, cannabinoid receptor 2, or CNR2 in a human. So we need this entry. We just basically need this ID right here for what we're going to do next. We need this unique identifier code, much like we talked about PDB IDs are kind of just arbitrary numbers and letters to identify something particular. We then need to go to another website to punch this information in. We can just Google Swiss model. This is the web service that we're going to use, Swiss model right on top. What we're going to do is go to, I believe, modeling. So we're going to go to this web service. We're going to go to start modeling. Up here, we're going to place that unique ID, which tells the program which amino acid sequence we want to use for what receptor. So we just basically take this UniProt KB, copy this code, Command C, Command V to paste it, and it'll basically, it knows that that unique identifier code is all the amino acids in the CB2 receptor. So basically, these are all of the amino acids that are in the CB2 receptor using their one-letter abbreviation. If you don't know all 20 of the common amino acids, I would highly encourage you to just Google the structure of the 20 amino acids. And, the 20 amino acids are essentially different combinations of those are what make up any protein or GPCR. In CB, in cannabinoid, in most GPCRs, they're around 400 to 500 amino acids is how big a GPCR is. We're going to hit this button down here, search for template. So what it's doing now is searching now through the protein data bank to find a structure that has a similar sequence to what we just punched in. So it should pop up in this search CB2 receptor, the protein structures that we looked at yesterday. And we're done. That wasn't actually that long. Okay, so what we have is it searched through the protein data bank, and it's basically telling us that, so these three receptors where it says 100, 100, 100, it's telling us that these three PDB IDs have 100% similar sequence homology to the one we actually searched for. And this would be down here 94% sequence homology, 94%. So basically the percentage of amino acids that are the same in that receptor target. And of course, we want a CB2 agonist. Let's kind of keep that in mind. We wrote that down last time. There's 3 on the protein data bank that are CB2 agonists. So let's go through the 3 and see which ones we could actually use. So we've got 6PT0. 6PT0 is an agonist with, it says right here, it's an agonist with Win55212. So we could use this one. That's totally cool to use. We could use 6KPF. This one had the agonist AM841 bound to it. And we could basically use either of these 2 entries. I would imagine that, oh, here's 6KPC. 6KPC was the other one, but apparently there's not 100% sequence homology. I would prefer to pick something with 100% sequence homology. And for that reason, I think I'm going to choose 6PT0 is the one I like. It's our top entry. It's what we want. So what we do now is we're going to click Build Model. If you wanted to, you could check multiple of these and build multiple different models. But for now, we're just going to build one. And as you'll notice in the right-hand side of my page, it shows us that GPCR. And we can, the 3D modeling for this is actually pretty good. It's actually pretty good. Kind of curious. Let's see. It's actually pretty good. Okay, it's important to note that you can kind of see there's almost two different receptors stacked on top of each other. That's just to show us that the sequence homology predicted structure that it's giving us is basically the same as the one from the protein data bank. And that's a good thing. We want to make sure everything matches up. I mean, there's very slight differences, but when we really get into it, it's not a big deal. I just want to make sure there's nothing else is checked. I think nothing else is checked and we're all good to go. Yeah, so if I check another one on the left-hand side, it'll just stack those structures on top, on top, on top. So here's it with 3 structures. And I can uncheck that to give us 2, and then 1. Okay, we can go to, let's build our model. You could do this, I think if you have a GPCR that has an unresolved crystal structure, doing a method like this is actually better than going to the AI predicted structures from AlphaFold. I think this is a choice I would choose to go over better than AlphaFold. And this is really nice. So you guys are probably wondering what the heck are these like gray, these dots that are that span this position. So all GPCRs are located in a plasma membrane. Plasma membranes are generally made of lipids that are hydrophobic. They're hydrophobic things, which means they don't like water. They're typically lipids. So a GPCR sits inside of a lipid bilayer, and what this these gray dots that span the helices is just showing the exact position that this would sit inside of a lipid bilayer. If you were to look this up. And I think that's actually nice. It's really useful to kind of see how that sits in a lipid bilayer. And as we talked about, GPCRs typically always, all GPCRs usually bind cholesterol, and that's what these molecules on the side are. And cholesterol is a very important compound that we use in our bodies all the time, right? Remember, cholesterol is not always a bad thing, right? Looks like anything in science. So, something interesting that I kind of want to point out with this little schematic is that the reason, so remember the tag thing that I talked about, the way to tell the back and the front of the receptor? The reason the tag is not considered one of these 7 helices is that notice how the tag is right here, and it's not, because it's located right here, it's actually below the lipid bilayer. So this part of the tag would actually be inside of the cell that separates the, so this would be the outside of this. So this is biology. Maybe look this up if you're kind of confused what I'm talking about. But this part of the receptor is in the outside of the cell. This part of the receptor sits on the lipid bilayer. And this part of the receptor sits inside the cell. So because this tag is located inside the cell, it's not considered one of those 7 transmembrane helices. And I use that tag oftentimes to figure out the back and the front of the receptor. So if I'm looking at the tag as so, this is the back of the receptor. So if I rotate it like this, I'm looking at the front of the receptor. And then what I can now do is if I click on model, I can get it in the PDB protein data bank format that this is the format that we want it in order to actually use it as a functional structure. And it downloads right there. We can open up Maestro. I hope you guys have Maestro or have downloaded. You can do this with Autodoc Vina, the free version of Maestro, of course. But if you're just here to kind of like go on for the ride and see how stuff works, you don't have to follow along. But I think it's beneficial if you're trying to actually learn how to do in-silico drug modeling to follow along. Okay, so we have Maestro opened. We also need that, we need this also open. You literally just take the structure and drag it into the workspace for Maestro, kind of like how we did it with the AlphaFold structure. So click, drag, and it gets dropped right in there. And that is beautiful. So what have we effectively done is we've replaced fake regions of protein that were used to crystallize the receptor with real regions of protein, amino acids, kind of a colloquial thing we could think of them as. So anyways, as before, I'm going to click the style toolbox and click ribbons. Okay. And this is beautiful. We have actually how a CB2 receptor would look without any fake regions of protein. Free way to do it. Thank you, free services like UniProt and Swiss Model. You're beautiful and amazing. So whoever wrote those services, thank you. Okay, so to get the ligand to show up inside the active site, I'm going to click L. And I'm going to click Style. You can either use the van der Waals to see them very large or the ball and stick model. I prefer ball and stick model. If you click L here, it'll take you to each one of the ligands. This is, of course, the active site where the drug or ligand will bind. But if you keep clicking L, it'll take you to the other biomolecules bound, which are the cholesterol molecules. Because we're going to be doing the way I'm going to model a lot of this stuff, it's going to be a static frozen system, not a dynamic system that moves, much like if you guys are familiar with molecular dynamics. I'm actually going to delete the cholesterol molecules just to make things simpler to see. So if I click up here, instead of atom, click residue, I can click one of these entries, go to edit, cut, click the entry, edit, cut. If I click L again, it'll take me to my next ligands. Click, edit, cut. Now we have one more. Something to make a side note, there's a lot of dimensions to ligand receptor binding, and one of them is that cholesterol binds to what are called allosteric binding sites on the receptor. An allosteric binding site just refers to any site that is not the orthosteric binding site. And remember, the orthosteric binding site is where the natural endogenous compound that your body synthesizes to activate the receptor binds. So in the case of CB2, that would be 2-arachidonoglycerol or anandamide, which are also the endogenous ligands for CB1 receptor. For serotonin, for any serotonin receptor subtype, this would be the molecule serotonin, and so forth. So I'm just going to delete the... If I were doing a molecular dynamic simulation where the system is moving in 3 dimensions, I would want to keep the cholesterol molecules, as this would be representative more of a real dynamic moving system. But because I'm not, I'm just kind of cleaning up the workspace. Okay, so now we have this very beautiful GPCR that has correct sequence homology and doesn't have any fake regions of protein. That's just beautiful. I love that. So anyways, the next thing we want to do is do what's called a protein prep. I don't think you can do a protein prep with the free version of Maestro, but I still want to kind of take you guys through how that works. Generally what I'm going to do in a protein prep is I'm going to relax the ligand receptor conformation. And the analogy I like to make for a relaxation is that, like, if you have my wife and I have a 4.5-month-old infant now. Generally, I guess, like a toddler or an infant, when they're in this really, like, crying or excited state, they tend to be high energy. And then when they're, like, very chilled out and relaxed, this is the equivalent of performing one of these relaxations. It kind of represents something at its, like, chillest, lowest energy ground state, if that makes sense. This would kind of be like, if you guys are familiar in organic chemistry with gauche versus eclipsed conformations of, let's say, like ethane, these types of things. So trying to get it at its lowest energy ground state, that is its relaxed state. So up here, if I go to tasks and I go to protein prep wizard, okay, all I want to do is relax the protein. So I'm going to go to refine. I don't really need to do, so what optimize does is sometimes when you get GPCRs and they are not prepared this way, they will have incorrect atom typing, which means that, for example, like a carboxylic acid will still have a proton on it, but we know that at the pH of a neutral pH of 7.4 biological pH, a carboxylic acid will be deprotonated, as carboxylic acids typically become deprotonated at pH 2 or 3. So that's kind of what this will do. This will place all the amino acids in their correct protonation state. I'm gonna run it even though I don't really need to, because the UniProt would have already done that for us, but I'm gonna run it anyways. And I just click optimize. When you run a job in Maestro, the job appears up here, and it's saying that it's performing a protonation, basically a protonation job to make sure the amino acids are in their correct protonation state. And this should run fairly quick because it's already in the correct protonation state, but we're going to run it anyways. If you want to monitor the job, you can double click a job and that'll take you to the actual job that is being run. Okay, and then it says finished right here, so it's done. Whenever a job finishes and you click table, it'll give that job a new entry. So this is before we did the protonation. This is after we did the protonation. And the last thing we need to do in that protein prep wizard, whoops, so many things running right now. That's okay though. This is science, and science is what we do on this channel. Okay, for restraint, so basically now what we're going to do is, now that the protonation state is correct, we're going to do that relaxation, was kind of, the analogy was like a really hyper child to a really calm child, or it can be an adult too. Okay, I'm going to change I'm not going to talk about force fields now, but typically the latest and greatest force field right now in Maestro is OPLS 4. I'm not going to talk about force fields right now though, but minimize. That's what we're doing. We're minimizing this. You can also do things like remove waters, but crystallographic waters in this specific receptor CB2 are not very common. In some GPCRs, there are waters that occur in the binding site, but because the GPCR is made of a lipid bilayer made of lipids, which are generally pretty hydrophobic, you don't really see a lot of waters in GPCRs, although there are always exceptions where waters do become important in some GPCRs. There's a very conserved sodium binding site in some GPCRs where water is really important, but for this particular GPCR, it's not important. This minimization shouldn't take too long. We can just monitor the job if we want, see it's running, atom typing, cool. The sort of workflow we're going through right now is, how to build our protein correct and get it ready for this virtual screen that we're going to run to discover new ligands. So the job is finished, and if we go to table, that'll appear in our workspace. If you want to compare the first structure to the structure that we just relaxed, if you hold Control and click the entry, it will appear. So notice how if we do the overlay, the two structures are very close, and that's because all we did was relax the structure. Given that in a crystal structure, the structure theoretically is in its relaxed form, the relaxed form that we get in Maestro shouldn't be that much different from the relaxed crystal structure form. So we get both those structures. Notice how they're very similar. You could probably you could get away without relaxing the structure. If you don't have access to Maestro, you could get away with this and do this in Autodoc Vina. You could do this for free in Autodoc Vina. So notice how there's not much difference. I'm not gonna be a stickler about these subtle differences. Oh, what's funny here is in this tyrosine amino acid right here, in one of the structures, it's missing the hydrogen coming off. And then in our relaxed structure, it has the hydrogen. So when it built that structure, it just left the hydrogen out, but with the proper, that's something that the protonation job would have fixed. I can just show it again if you would like. So here's that tyrosine in this one without the hydrogen, and then when you plug in the optimizer to get the correct protonation state, it puts the hydrogen on, which should be there, And I think that's where I'll leave it for today. Kind of in summary, what we did today was look at how to further prepare and refine our structure for an actual ligand drug discovery, which is what we'll get into next time. With that being said, I hope you found this video informative, and I hope you're enjoying this series. And this can be applied for any GPCR. I'm not going to encourage this, but if you want to, you could follow the same steps for NMDA receptor, CB1 receptor, these types of GPCRs. Some of the GPR, you could build a sequence homology structure for GPR55, like a lot of people are interested, or opioid receptor, but I'm not going down that route. Anyways, I look forward to seeing you guys again soon, and hope you're enjoying. Bye.